Hey everyone, welcome back to my daily coding series. Today is episode 92. So I'm going to continue with where I left off yesterday. So yesterday I tried this problem, just kind of went into it blind. Um, so now I've looked at the drawing solution for it in this video, and I know it's basically it's a pretty popular algorithm that you learn in school called Prim's algorithm. Um, I got really close yesterday. For those of you who watched it, with my first guess, basically my first guess of how to solve it was this algorithm. Um, you would pick a random point and then make the smallest edge from that point, and then from that point pick the smallest edge that that point has and keep going. The difference between, so that's not right. That's what I thought might work. Um, and then for this, so what you actually have to do is start with a random point, pick the smallest edge, and then between not only that new node's edges, but also keep the original edges that you had and pick the smallest out of those. So the number of edges that you can pick from grows. It doesn't just change to the new node. You just add the new node's edges. Um, the second thing I tried in the video was kind of more like Kruskal's algorithm, which basically you just forget the nodes. You basically just pick like the smallest edge that exists in the whole graph, as long as it doesn't make a cycle. And I was trying to do that one, but the problem was, um, basically you can pick an edge as long as it doesn't create a cycle. So it's kind of hard to determine if it creates a cycle or not, because sometimes you have to create an edge between two already visited nodes, as long as those nodes are parts of different trees. So you just can't do it if they're in the same tree. And I still don't really know how to do that. I looked it up and it says something with, it's called union find. But anyway, so I'm going to attempt to solve this now with Prim's algorithm the right way, where you just grow the number of possible vertices that you have. Okay, so first what I'm going to do is build a graph, which I'll represent as an adjacency list. And after that, I will start with random node, add node to heap and visited. So we're going to have a visited set, and that's like our stop condition, as well as so we don't make any cycles. So in Prim's algorithm, you can assume that every node you're visiting is a part of the same tree, because you have to select edges from a node you've already visited. So you can never, like in this case, you would never be able to go from this point to this point, and then let's say on the other side of the graph connect this point and this point. You only can move from these 2 points. So therefore you can assume that every node is part of the same tree. Okay, so we're going to add that node to visited and add it to heap with cost of 0. By the way, so yeah, I'm not going to explain what the problem is because it's in my other video, but it's basically like a minimum spanning tree where you have to, I guess I'll just explain it. So you have a graph, and you have to so you have points on a 2D grid, and you have to connect those points in such a way that the least distance is used. Okay. All right, so once we have that, we want to add every neighboring edge to heap. Yeah, so we want to add every neighboring edge to the heap. And then Okay, so I guess this is kind of like, so I'll put it in a loop. So while the length of visited is less than length of points, so while we still haven't visited all the points, what we want to do is pop the minimum weight edge from heap that isn't that doesn't have node in visited. So we're going to continuously pop a weight from our min heap, which basically is just going to get the minimum value edge. And then yeah, so in that case, it'll be just the starting. And then we want to add every neighboring edge to the heap. And then add node to visited. So for instance, let's say we'd pop the first one from the heap because we only have one in the heap. Then this is true. So then, yeah, so then we pop, and then every neighboring edge, so for instance, this one, we would add it to the heap, and then we would add 0 to visited. And now with this one, we'd pop this one from the heap, we'd add its edge, and then add this to visited. And now with this one, we would, well actually, so this is already the complete graph. So really what we would do is have all the edges from 0, 0 to every point. So we'd add all of those edges to the heap, and then we'd add 0 to visited. So now all of these edges, so from 0 to every point, is in the heap. So then we would then pop the smallest one, which in this case would be this edge right here, right? And then from the new node that we just connected the edge, we're going to do the same thing where we add every neighboring edge. So then from this to every point. So now we'd have 1, 2, 3, 4, 5, 6, 7 minus this one. So we'd have 6 possible choices now. So we could do 0, 0 to any point, or we could do 2, 2 to any point. And we just keep doing that. So I think that's the structure of it. And yeah, this isn't meant to be like a tutorial or anything. This is me problem solving it. Okay. So first let's build a graph. So we have points like this. So so 4 points in points. Actually, okay, yeah, so for this one we want to do the double for loop. So we're basically, so like 0 has to connect all of these, 2 then has to connect all of these, 3 has to connect with these, etc. So it's kind of like a n squared behavior. In the range length of points, and then we're going to have for j, which goes from I to length of points. And then P1, P2, so these are the 2 points, will be points of I and points of j. Okay, so now I'll just make a graph, which is a dictionary. Then I'll say graph of P1. Well, I guess let's say if P1 not in graph, then we'll say graph of P1 equals empty list, and then if P2 not in graph of P2 equals empty list, and then we'll say graph of P1 dot append P2, graph P2 dot append P1. Okay. So what this is going to be is the key will be a point and the value will be its neighbors. So let me just print the graph here and make sure that looks good so far. Okay, so I have the points. So right now, just to explain this, so right now in the graph, I'll just do it without comments. So in the graph right now, we have, for instance, 0, 0 as a, like, that as a key, and then that goes to a list with a list of lists. So like this, for instance, and then the rest. So the problem with this is you can't have a list as a key of a dictionary, because a list is mutable and dictionary keys have to be, as it says, hashable, which means it has to be immutable, is my understanding. So I'm just going to convert these into tuples. So we'll have points instead of lists, we'll have tuples as the points. So that should work because tuples are immutable. Okay. Yeah, so now we see that 0, 0. Okay, it's connected with itself for is it in range of I plus 1? Okay, so 0, 0 is connected to 2, 3, 2, 4, 4, 2. That's good. 2, 2 is connected to, yeah, so they're all connected to each other. And that's what we want. Yeah, so they're all connected to each other. Okay, so this graph looks good. Yeah, and let me just make sure the last, yeah, okay. So now this is the adjacency list. It's basically a complete graph where every node is connected to itself, or connected to every other node, excluding itself. All right, so now we built a graph. So now we will have our random node, which I guess will be, so we'll say like start equals points of 0, and then we'll just put it as a tuple. We also need to make a min heap, so I'm just going to import that real quick. So we'll put, so what our heap is going to have inside of the heap, just like last episode, what I was trying to do. So we're going to have the cost and then the node. Last time I said like start node and end node, but we don't need the start node. So we'll just have it like this. So for instance, at point 0, 0, we'd have 4 edges. So from 0, 0 to 2, 2, the cost is 4. So we, in our heap would be 4 and then node 2. And then from 0, 0 to 4, 2, the cost would be 6. So it would be 6. And then, and yeah, this node is actually a point. So it would be 2, 2. And then 6 to the point 4, 2. So it'd be like this. So we have the cost and then the node, where the node is a tuple of coordinates. All right, so heap q, heapify min heap. And in here we want, so what is start? It's a point. So we want 0. We probably, okay, so we want a tuple like so. And start is a point. All right. Okay, so we've created the graph and now we have initialized our variables. I'm going to get rid of start and I'm just going to call this tuple points of 0. Okay, so now we've created the graph and we've initialized our variables. So now we're going to start this here. So I'm just going to move this down for reference. So we did this and then we did that. Okay, so we're going to keep going. And let's imagine if we just have one point in the graph, which is possible, then our visited will be 1 and our length of points will be 1. So we'll exit out, and the cost, we also need to initialize the cost. Our cost will be 0, so that'll work. Because if there's no edges, like if there's only one point, we can't even make an edge, so the cost should be 0. All right, so what we want to do is heap q dot heap pop from min heap, and this will return a tuple. So I'll say, let's do total cost, and let's say cost and point. So we're going to get the cost and the point from the min heap. Now we have to make sure, okay, let's just not worry about the visited for now. So this is the minimum one, and if we assume that it's not visited, now what we want to say is for neighbor in graph of point, we want to add all of them to the min heap. Yeah, so what's neighbor? Neighbor is another point. So let's calculate the distance. And let's define that as it's the absolute value of something plus the absolute value of something else. And this is the change in x. So that would be neighbor of 0 minus point of 0. And then change in y, neighbor of 1 minus point of 1. And so this is going to be a tuple. This is going to be also a tuple. So that's okay. So this is the distance. And then what do we want to do with that distance? Well, we want to add it to the heap. So we'll say heap q dot heap push into min heap. We'll push so now we're going to push that thing I was talking about with cost and node. So the distance is the cost, and the node is neighbor. Right. And then also what we want to do is add to total cost somewhere. So if we're doing, so like this is the one that we selected, and then this is all of the possible ones that we had. So for the one that we selected is the one that we want to increment. Okay. Sorry, I had to sneeze. Okay, so all right, so now where does visited come in? So we're going to extract from the heap, and probably if we've already visited, that point, then we don't want to do that edge, I think is where that comes in. So we just keep popping from the heap until we get a point that is not visited. And then in here, after all of this, we want to add visited.add point, I believe. So after we've added all of its neighbors, then we add the points. Yeah, and we could do that wherever. Okay, so I wrote a lot of code, so I'm probably missing something somewhere. So maybe what I could do is just run it and see what error I get. Well, I'm not returning anything. So we would want to return, in this case, total cost. Okay, so the first test case got accepted. Let's see if I fail on one of the other ones. Okay, so this is the case where we have one. I'm just gonna put it in this window. So in this case, we have 1 point. So my understanding is that this should skip. So I don't know why it's even in here. So let me print. Oh, does visited? Oh, visited is empty. Whoops. We have to have visited. Inside the set, we need. Do we add it to visited? No, I don't think we do. Yeah, because we want to explore it. It's unexplored. So I think the thing is, it's never being added to the graph because this is for I in range from 0 to length of points, and then this is from 1 to length of points. So if length of points is 1, then this will never execute, which is okay. It may just be worth adding an if statement for this, just because I think this code is fine. I like how this code is, and we don't really want stuff to connect to itself. That would go poorly with the problem. But we also need it to not be invisited, so I would say this probably merits an if statement. So if length of points is less than or equal to 1, then we can return 0 for the total cost. So that should fix this edge case. Hopefully the general cases work. And then I just deleted the visited set. All right. Yeah, so normally with problems like this, you actually do add the starting node to visited right away, but in this one, I guess you don't because you need to actually do it. Okay. Yeah, so we solved it. So that's nice. I'm just thinking now so this builds the graph. I like that together. This is initialized it. Maybe, so this stuff, like the order doesn't really matter that much. We definitely want this. And then for this point, we can just do the order kind of however. So I'm just going to do it like this. All right. Okay. All right. So now, yeah, that's good. I'm glad I was able to get that. So now I'm just going to look on LeetCode and see if it passes the judge there. But yeah, this was a good algorithm. I feel happy that I did this one. I got pretty close. So what would I need? What question number is this? So I did have to look up the solution though. So what would I need to do it myself without? I mean, I got pretty close, so I'm not too mad about it. But I would say that, yeah, I guess just the realization that you should consider the previous edges as well and not just the one that you travel to. All right, so let's check out this. See if this works. All right, it got submitted. It's not really memory efficient, but all right, awesome. So thank you guys for watching. That was episode 92. And I will be back tomorrow with 93.